Okay, now that we know how to find the focusing point of a thin lens, we're now able to draw ray diagrams for images formed by any thin lens. For example, let's start with a convex lens. Okay, that's a lens with both sides bulging out like this. So this is a side view of that lens. And as a symbol of a convex lens, we draw something like that. Okay, so you have a symbol like this. That means it's a convergent. It's a convex lens that curves out like this and like that. Okay. Again, I need rules so that I can guide the light rays to where they're supposed to be. Okay. One of these two rules concerns about any beams that are parallel to the optical axis. Okay. So if a beam is parallel to the optical axis, where does it go? Well, here. According to what we just studied before, any beam, assuming it's near axis, okay, that is parallel to the optical axis, will end up crossing what? The focal point. Okay, crossing the focal point. So that is the our first rule. Of course, conversely, if I draw a beam that goes through the focal point, then it's going to end up parallel to the optical axis afterwards. So if I draw a beam, say like this, for example, passing through the focal point, it's going to end up parallel, like this. Okay, so that is one of the rules. The second rule concerns about any beam that is aimed at a particular point right in the middle of the lens. It's called an optical center. Optical center. Imagine a beam like this. Okay, now this beam will be refracted twice before coming out. But there is something special about a beam pointing towards the optical center. Okay, what I can draw roughly is something like this. Alright, let me draw the local tangent. The local tangent. And as a result, I can also draw the local normal line. So this is the incident angle. And then you have an outgoing angle, like this. And then it's going to get refracted here again, okay? Here again, and it's going to come out eventually. It's going to come out. Now, the way I draw it, you can see that this plane and that plane are roughly parallel to each other. Okay, they're roughly parallel to each other, and therefore, as an approximation, I can think of the behavior of this beam to be really equivalent to a beam that passes through a parallel slab of glass with no curves. Okay, so basically here is the first surface, here is the second surface. They're roughly parallel to each other. It's just like having two parallel surfaces. So this is a glass slab between here and there. This is air, this is air. Now this case is rather simple. You can see here. I got a beam coming in, making an angle theta 1 with the normal, and it makes an angle theta 2 with the normal, and then it's refracted again. Theta 2 reverses back to theta 1. Okay, so you got a beam coming in and a beam coming out. These two beams are obviously parallel to each other. Okay? They're parallel to each other. There is no focusing effect. That is why, you know, a plain glass pane with parallel surfaces will not cause any focusing or anything. I mean, otherwise it would just make no sense, right? You look out of the window, you see some funny images going on, but that's certainly not the case. Light just simply goes parallel. Now, so this beam, the only thing that really happens to this beam is that it's getting a little shifted without going in a different direction. It's getting a little shifted from here to there as it comes out. How much does it get shifted? Well, that largely depends on how thick this glass pane is. But I'm assuming that this is a thin lens, so the total thickness is almost zero, which means that even the displacement, the amount of shift is almost equal to zero. So not only is it parallel, but also has virtually no shift. Therefore, as an approximation, we say any beam that is aimed at the optical center simply goes right through. Okay, no deflection and no shifting. Okay, so these are two rules. So for example, if I were to draw another beam aimed at the optical center right here, what it's going to do? Well, it simply is going to go right through, like this, okay, as an approximation. So these are the two rules, one concerning the focal point, the other concerning the optical center. Once we have these two rules, it is easy. It would be easy for us to finish the ray diagram, so we can trace the light rays coming from the object to find where the image is. There are several possibilities. Just like the case of a concave mirror, there are several possibilities depending on where you put the image, put the object. Okay, the first case is when we put an object pretty far away. The object distance between, which means the distance between the object and the optical center, P, is greater than two focal points, two focal lengths. So here's F, right? This distance is 2F from the optical center. So suppose I have an object. I have an object placed quite far, say here. Okay, quite far on the optical axis, more than 2F. So this distance between here and there is P greater than 2F. I want to know where the image is. Okay, now I don't have to guess. I can draw a ray diagram to find out. I'm going to draw two light rays coming from the tip of this image, of this object. After going through the lens, let's see where they go. Okay, what's your first light ray? Well, how about light ray passing through, say parallel to the optical axis? Okay? Parallel to the optical axis. Where is it going to go? Well, it's going to go through the focal point, as usual. Focal point. So that's ray number 1. What about ray number 2? Well, there are different choices. You can aim at the focal point here, and so it will come out parallel. Or you can also aim at the optical center. It's probably easier to draw that way. What's going to happen to that light ray? It goes right through, undeflected, goes right through. Okay, so you see these light rays will converge at this point. This is therefore the location of the image. What is the characteristics of this image? Well, first of all, is it real or is it virtual? Well, you see, IQ light rays pass through to converge at this point, and this is the correct side to form the image, right? It's behind the lens. Light rays are supposed to go through the lens, not reflected. So this is the right side, the correct side, and it's a real image. So it's real, okay? Obviously, it's upside down, so it's inverted. What else? Smaller than the object, so it's magnified. Okay, you see, this is really the same as the case of a concave mirror. Right? For a concave mirror, when P is greater than 2F, you get the same deal. A real inverted magnified image, except of course in that case everything is reflected, so the image is formed on the same side as the object. Here it is formed on the opposite side, as it should be for refraction. Okay, now let's bring the object a little closer. Okay, so this time I'm going to put the object between 1F and 2F. Okay, so this is 2F, this is 1F, right? I'm going to put it between 1F and 2F, so it's here. It's here. Where is the image going to be? Well, again, let me draw the light rays. Okay, light ray number 1, parallel to the optical axis. I know that it is going to cross the focal point here. Another light ray aimed at what? The optical center, like this, right? It's going to go right through. Okay, once again, these two light rays will meet over here. This, therefore, is the location of our image, right here. Okay, you take a look at these two images. They're not that different, this one and that one, except this one is bigger than the object. This one is smaller than the object. Okay, so we can write down the characteristics of the image. It is real, right? It is inverted, and it is magnified. Now, if you recall, the image formed by a concave mirror with an object distance between 1F and 2F, you get exactly the same thing. Real, inverted, magnified. So you see, we start to suspect that a concave mirror really behaves analogously to a convex lens. Okay? one through reflection, one through refraction, but the image characteristics would be the same. Now, you recall for the case of a concave mirror, if you put an object within one focal length, what do you get back then? Well, you got a virtual image, right? Which is the right side up, okay? Right side up, but virtual image. Do we get the same thing here? Well, let's see. Let's draw it, okay? I have an object within one focal length, so it's here. It's here, within one focal length. I want to know where the image is. Again, let me draw two light rays. Okay, the first light ray, I'm gonna aim. Actually, let me draw a line that's parallel to the optical axis like this, and I know where it goes. It's gonna go through the focal point here, right? The focal point here, so it goes like this. And there's another light ray. Another light ray. I'm gonna aim at the optical center like this. It goes right through. Now, you look at it from this angle. What do you see? You see two light rays going this way, going that way. There is no way they will ever converge on that side, right? But to your eyes, these two light rays appear to originate from one common point somewhere here. So I'm going to extend these light rays backwards, and you find that they seem to originate from the same location here at this point, and this, therefore, is the location of what? A virtual image. Okay, just like the case of a convex, of a concave mirror, here you get an image that is virtual, that is upright, okay, it's not inverted, and that is magnified. Okay, can you give me an application of something like that? Okay, so basically you hold a convex lens, right, in front of you. Okay, here's the object. This is you. Okay, you want to take a closer look at this object. What do? You take a convex lens, put it really close to that object, so that the object is within one focal length of the lens. And then you look through the lens. You don't see this object directly. Rather, you see an image of that object here behind it, bigger than the object itself. Now, what do we call that setup? Yeah, we call it a magnifier, right? That's how a magnifier works. So a magnifier really is just a convex lens, okay? And you have to put it close enough to the object so that it is within one focal length, so it acts as a magnifier. You can try to take that magnifier and bring it further and further and further away from the object. So you're going to get into this situation and that situation, and then you look through the lens. What you will see is something totally different. You will see something inverted, okay? Not right side up. You can test that for yourself. Okay, so you can see drawing ray diagrams are extremely important because it allows us to find the characteristics and location of the image under any circumstances. Okay, in the case of spherical mirrors, we had what's called a mirror equation. Now, what I'm going to do here is to derive something similar. It's called a thin lens equation. Okay, it's called a thin lens equation. A thin lens equation, just like the mirror equation, tells us the location and the size of the image that is formed by an object placed at a certain distance in front of the lens. It relates P, Q with F, the focal length. Okay, let's say I have an object here of height h. Okay, it is placed a distance P in front of lens. So here is the lens. Distance between here and there is P. Okay, as a result, you draw two light rays, one parallel to the optical axis passing through the focal point, another passing through the optical center O, undeflected. So they're going to merge here to form an inverted real image of size h prime from here to there. Okay, now what I want to know is how is P related to F and Q. Q is the distance between the image and the lens itself. So from here to there is Q. Okay, I want to find the relationship. How do I do that? Well, actually it's quite simple to do. All you need is really take note of a pair of a couple of similar triangles. Triangle pair number one. Look at this one and that one. Okay? In this one, I have h over p. Right? I have h over p. H over p. correspondingly, I have h prime over this distance, which is q. That's our first equation. Now, remember, I must get f involved. F is the distance between O and the focal point F. Okay, I must have this distance involved. And how do I do that? Well, let's look at this pair of right-angled triangle. This pair, okay? In the first one, I have h over f, the focal length between here and there. In the second one, I have h prime over that. Okay, h prime over what? This distance. What is this distance? Well, it's just total q minus f, right? Q minus f. Okay, so now I have two equations. All right, what I'm going to do is I'm going to combine them. Okay, I'm going to combine them. How do I combine them? All I have to do really is take this equation divided by that equation. You see, if you do so, h and h cancels, h prime and h prime cancels, and let's see what we come up with. Okay, so if you take this divided by that, you just get f over p. Okay, and the other side is going to be q minus f divided by q, right? Which I can write as 1 minus f over q. Okay, now what I'm going to do is going to divide everything by f. Divide this by f, this by f, this by f. That I get 1 over p equals 1 over f minus 1 over q. If you move that q over, you find that 1 over p plus 1 over q equals 1 over f. This is the so-called thin lens equation. And as you recall, this really is the same exact form as the mirror equation, right? It's the mirror equation. So no wonder the ray diagrams that we drew for the lens and for the mirror, for the concave lens, convex lens and concave mirror, really yield the exact same characteristics of the image, because the location and size of the image are determined by the equation here, and this lens equation is the same as the mirror equation. Okay, so from that you can also figure out the characteristics of the image without even drawing a ray diagram. You can see from right here. We can take a look at a couple of examples. You know, the magnification m is defined as h prime over h, of course. H prime over h, right? If m is greater than 1, the image is bigger than the object, and so on. But that is equal to, you can see here, q over p. Okay, now we can think about it this way. 1 over p plus 1 over q equals 1 over f. There is a certain distance p that you can put in front of the lens so that p and q are equal to each other. What is that distance? That is when p equals 2f. Okay? When p equals to 2f, q must also be equal to 2f, because 1 over 2f plus 1 over f in fact equals 1 over f, right? So when p and q are equal, but both equal to 2f, the magnification will be equal to 1. That in fact is the way, pretty much what I draw here. This is about 2f, right? And this is about 2f, so you see the size roughly the same. Okay, but if I put an object further away than 2f, okay, then p is greater than 2f, then q's got to be less than 2f, right? In that, then q over p will be less than 1, so that's why the image will be smaller. And you can see from the ray diagram that we just drew, okay, p greater than 2f, q is less than 2f, the image is smaller. On the other hand, if you put p ahead, less than 2f, p is less than 2f, then q is greater than 2f, so the magnification q over p will be greater than 1, and that's what you have here. Okay? Also, if I put p less than f, okay, then 1 over p numerically will be greater than 1 over f, right? And therefore, if you put that 1 over p over there, 1 over f minus 1 over p will be what? Will be a negative value. Okay, a negative value, that means q is negative. Now, again, what does a negative image distance mean? It means the image is formed on the wrong side, and you will get a virtual image. Okay, that's what it means, and it's exactly what happens when p is less than f. You get a virtual image on the wrong side, which is the same side as the object in the case of a lens. So everything works out. The thin lens equation gives the same answer as the ray diagram. Okay, now we're not quite done with this chapter yet. We're also going to look at another type of lens, which is the concave lens. And we also look at what happens when you have more than one object, more than one instrument, such as two lenses or one lens and a mirror, placed together. and we can see what happens. So there will be a third part of this lecture, but it's